You are currently the only
Hello.
person in this conference.
Hi, Surab, could you hear me? Okay, good. I don't know what happened with Zoom, so probably Canvas is better. Yeah, I'm trying to record this one, and you can see that this is recording. So, but yes, but is recording. So so we will see what is the quality of the videos for this class. So we wait for a couple of minutes for the others, and then we will continue our lecture. All right. So good afternoon. I'm sorry for this mess with Zoom. I don't know what happened because I was waiting and it seemed to say that there's no one coming. So I'm just going back to this Canvas business. It is a little bit harder, but now Zoom has a problem. So for this one, I'm also recording. Yes. So let's see what is the quality of this recorded lecture. So let us continue our lecture. So now we are at 2:10, and we will continue our class. I mean, until 3, right? Or you want to stop at 2:50? You have any classes after? So you okay. Okay, good. So we continue until 3, right? So let us continue our last Milgram proof, last Milgram theorem proof. Proof. All right. So last time we said what? We said that we have a bilinear mapping, BUV, right? And then we say that, okay, we have an L, which is a linear operator on H, right? So which means that L is going from H to R, and B is going from H times H to R. And now we say that, okay, there exists a unique. So if B and L satisfy some condition, then there is a unique U such that BUV will be equal to LV for all of the V in H. This is the Milgram theorem, right? So the Milgram theorem says that you have a bilinear mapping and a linear operator. So the bilinear mapping will be acting on two variables, V and U, and the linear operator will be acting on only the variable V. Now, the claim is that, okay, there exists a unique U in H, of course, such that BUV will be equal to LV. All right. So from the previous class, we observed that, okay, so if we fix a U, fix an arbitrary U, then the mapping V going to BUV, all right? So this is map H to R. So you fix U, for each V you have a value B UV, right? So this is going to be linear, right? So it's a linear map from H to R, right? Right? So you see the point, because B is bilinear, in U and V, meaning that for fixed U, or then B is linear in V, right? And for fixed V, then B is also linear in U, right? Right? Any questions? Right. So now we know that, okay, so now the value of this U is going to be fixed, and we consider this mapping from V to BUV with U fixed. All right. In other words, I'm gonna define an operator B tilde, which is a V, and this is equal to BUV. And this U is a fixed vector, right? So this is going to be linear. All right. To see this clearer, you're gonna have what? You're gonna have BV theta V will be BUV. You remember that V is always fixed. All right. So now, for instance, you're gonna have what? You're gonna have alpha V1 plus alpha 2 V2 will be B of U alpha 1 V1 plus alpha 2 V2 and this is going to be B of U V1 alpha 1 plus alpha 2 BU V2, right? In this case, U V1 V2 are in H. Remember that from the previous class, we suppose that H is L2 so that we can simplify the proof, but the proof is true for all choices of Hilbert spaces H, right? And alpha 1 and alpha 2, they are real number. I remember that we're considering this a very simple case in which H is L2. All right, so I explain again. If you fix U, then this is a linear function in V. All right, so with this fixed U, you're gonna get a linear mapping. B tilde V will be BUV, right? So you can see that this is linear clearly from this algebra. You're gonna have B tilde of alpha 1 V1 plus alpha 2 V2 will be BU alpha 1 V1 plus alpha 2 V2, right? But this is linear in the second variable, meaning that you can pull out V1 and V1, alpha 1 and V1, and alpha 2 and V2, right? So this gives you alpha 1 BU V1 and alpha 2 BU V2. So B tilde is linear. This is my first remark. For a fixed U, this will be a linear operator, right? So now what can, so my next question is B tilde a continuous operator? Right? So our first observation is that this is a linear operator, of course. Is it a continuous operator? This is a continuous mapping. Yes, Abdullah, you have some idea? Is it continuous? Yes. So Abdullah said that this is yes. And the answer is correct, right? So this is a continuous operator. Why? So to show that a linear operator is continuous, what is the equivalence of the fact that the linear operator is continuous? Right. So Tyler's answer is correct, right? So according to Tyler, so we're gonna need to show that B tilde is bounded. All right. So because this is linear, since B tilde is linear, right? So we know that, okay, for all of the linear operators, for all of the linear mappings, B tilde is bounded is equivalent with B tilde is linear, right? So boundedness is equivalent with linearity. So we need to show that B tilde is bounded, right? So how do we show that? How do we show that B tilde is bounded? Right? So to show that B tilde is bounded, right? So we have to show that there is a constancy such that the norm of B tilde, so that B tilde of V is going to be smaller than the norm of V, right? So how can I find this constancy, right? So to show that this is about the linear operator, you're gonna so by definition, right? So this is definition. We're gonna need to show that the absolute value of B tilde is going to be smaller than C, the norm of V, right? So how do we show that? This is by definition. Uh, so yes, so now so Abdullah has a good idea, but but the definition of continuity, the limit definition of the continuity will help us to show that b theta is continuous. But we show something different. We show that b theta is bounded. So b theta is bounded is equivalent with b theta is continuous, but here but here showing that b theta is bounded is indeed easier than showing that b theta is continuous, right? So now what we are trying to show is that b theta is bounded in the sense that there is a constant c such that the absolute value of b theta is going to be smaller than c times the norm of v. So how do I show this? Of course, we're going to use definition, right? We're going to use definition, but not the limit definition of continuity. So what is b theta of v? So b theta of v will be this guy, right? So we go back to the definition of b theta of v. B theta of v will be this guy, b u v. So this guy is smaller than c times the norm of v, right? So now we have to find this c. Right? But notice that in this case, the the u is fixed. So now my question is simpler. What is this guy c? So now we have to go back to the condition that we have. Right. So Jonathan got it, right? So Jonathan, idea is to go back to the definition of B, right? So you have B u v is going to be smaller than what? It's going to be smaller than a constant alpha times the norm of u times the norm of v, right? So then what is the c here? The c here will be this guy. So the c will be alpha u, right? So in this case we fix u, right? In this case, notice that u is already fixed, and we consider only v, which is moving, right? So again, so the idea is the following. The idea is now, let us look at the bilinear form BUV, right? In the BUV form, you see that, okay, if I fix u, then I'm going to have an operator b theta of v. So u is now a constant vector. Of course, this is a linear operator in b theta, all right? So this is a linear operator in b theta by definition. Now, I want to show that this b theta, I know that this is continuous. How do I show that this is continuous? In order to show that b theta is continuous, I'm going to show that this b theta is bounded. Right? So because this b theta is linear, so continuity is equivalent with boundedness. But the fact that b theta is bounded is for free, right? Because in order to show that b theta is bounded, I'm going to need to find a constant c such that the absolute value of b theta v is going to be smaller than c times the norm v. Now, by the hypothesis, I know that this b is going to be smaller than alpha times the norm of u times the norm of v, which means that I can choose this alpha u to be the constant c, right? Remember that this is fixed. All right. Any questions? All right. So next step, we know that b theta of u of v will be u fixed, right? So b theta will be bounded and linear operator, bounded and linear mapping. Right, and in this case, H is L2. Right, so what can I say about B2 alpha? So if you see a linear mapping, so now we fix this U, right? And this become a linear mapping for V. So we know that B tilde is a bounded and linear mapping, and that now, so in this special case, we consider H3L2, right? Now, for any linear operators on L2, what happened? What can we say about any linear operator on L2? No, this is what we just learned from the previous. Yes, Tyler. Yes, the dual space has nice property, but what is it? Right, Jonathan got it. So you want to use Riesz theorem, right? Riesz theorem. So which means that you want to have a W in L2, all right, such that this can be presented as the product of D, right? So suppose that this is D dimension, right? I explain again. So this is Jonathan idea, right? So the idea is the following, because H is L2, which is Hilbert space in the D-dimensional space RD, we can use Riesz theorem. So any B tilde, so B tilde is bounded in a linear mapping, meaning that B tilde will be on L2 star, right? So the dual space of L2 or the dual space of H, right? So by the Riesz theorem, there is a W which is in L2, right? Such that B tilde of V can be written as the inner product of W and V, right? So in the Riesz theorem we have P and Q, right? So Riesz theorem we have P and Q, right? But here P and Q they're the same. Yeah, because one half is a dual of one half. Sorry, it's equal to 2, right? Because one half plus one half is 1, right? So by the Riesz theorem, there is a unique W in L2 such that you can write B tilde V to be the integral of the product of W and V, right? So which means that there is a unique W in H, which is L2, right? So I'm just using H so that you can convert to the general case, right? So which is L2, such that PUV will be the integral on ID of Wx dx, which is a nice thing, right? Right? So to summarize what I proved, for each U, there is a unique W, of course, depending on U, right? On U, such that B UV is equal to integral on ID of W x Vx dx for all of the W in H, for all the V in H, right? I explain again. First, I'm gonna freeze the W, right? So this U will not move. It's a fixed constant vector, right? So I fix U. What happened when I fix U? When I fix U, I have a linear operator in V. Now I have a linear operator in V, and more than that, because B is bounded, it's a bilinear form, but this is bounded. B tilde is also bounded. So B tilde is bounded and linear, meaning that B tilde will be in the dual space of L2, which is H, right? We can use the Riesz theorem that we learned from the previous classes. The Ritz theorem says that there is a unique W in L2 such that this B tilde of V will be the integral on RD of the product of W and V, right? And then, in other words, if I free U, I can find a W such that the BUV will be the integral on RD of Wx, Vx, dx, right? And then the W will depends on U, right? Notice that because if I free one U, I'm gonna find one W, which depends on U. If I pick another U, which is different from the previous U that I picked, I'm gonna find a completely different W, which also depends on the U that I just pick up. So W has to be depending on U, right? So since W depends on U, we write W under the form of A of U, right? So which means that you have BVU is equal to integral RD of AU V dx, right? So for U there is an AU which is unique such that BUV is equal to integral RD of AUV dx, right? But this is the inner product on L2, so I can write this way, right? So the idea is simple. You fix this U, and the leftover is a linear operator and bounded operator on V. So the Ritz theorem said that okay, there should be a vector depending on U. So this has to be a function of U. So this is a U, such that this guy is the integral RD of AU V dx, and this is nothing but the inner product of AU and V. It's clear? Questions? Right. So this is right. So right. So now what we have proved in step 1 that is that for all of the U in H there is a unique AU by Ritz theorem such that BUV can be written as the integral on RD of AU V, right? So A with this guy dx, or this is also AU V, the inner product. All right. So step number 2, I'm gonna show that A is linear in U. So how do I show that A is linear in U, right? Any ideas? So far what we show is that, okay, we fix U and we use the fact that B is linear in V, right? So we use the following fact. So we use the following fact. We fix U, and we use the linearity in V, right? Of the operator of BUV. So what didn't we use? Right? So we use the linearity in V. So we are missing something that we haven't used yet. What is it? So you understand what I mean? So first I fix this U, and then because this is linear and bounded, I can use the Ritz theorem to show that there is an AU such that BUV is the inner product of AU and V, or this is the form of this theorem. Now, I want to show you that this A is even linear in U. How do I show that A is linear in U? All right. So to show that A is linear in U, I'm going to check back my hypothesis, right? So in the hypothesis, I consider this bilinear form, and I use the fact that this bilinear form is linear in V if I fix U. But there's something that I haven't used. What is it? So this is a bilinear form, right? Meaning that this is linear in V. And this is also linear in use, right? So this is what we use. And this is what we haven't used. We haven't used the fact that this bilinear form is linear in V, in use. So let us try to use this business, right? So what happens if I have alpha 1? So I want to show, right? So we want to show A of alpha 1 U1 plus alpha 2 U2 is going to be alpha 1 A U1 plus alpha 2 A U2, right? Where U1, U2 are vectors in H, and alpha 1, alpha 2 are real numbers, right? So this is what we want to show. We want to show that this new A is even linear in the first variable U. All right? All right, so now we're going to use the fact that B is linear in U. So how do I use it? So I'm going to have what? A of U1, U2, V. So I'm going to act on V. So what is it? Right, so now I want to use the fact that B is linear in U, right? So this is why I'm going to use this identity, the definition of A, right? I want to show that A is linear, meaning that I want to show that A, alpha 1 U plus alpha 2 U, alpha 1 U1 plus alpha 2 U2 will be alpha 1 A U1 plus alpha 2 A U2, right? Right? So I'm going to use the definition of A. The definition of A will be depending on B, right? So I'm going to pick a vector V, and I'm going to multiply it with A, and I integrate it. So I have the inner product, right? So how can I develop this expression? This is going to be equal to what? So this is going to be equal to B of alpha 1 U1 plus alpha 2 of U2 V, right? By definition. Because I have what? I have AUV will be BUV. So A alpha 1 U1 plus alpha 2 U2 V will be B alpha 1 U1 plus alpha 2 U2 V. Right? So which means that, okay, B of alpha 1, so because this is bilinear, so I can write this as alpha 1 B U1 V plus alpha 2 B U2 V. And this is what? This is alpha 1 A U1 V inner product plus alpha 2 A U2 V inner product. All right? So, but this is the inner product. So what I'm writing is integral on ID, right? Of A U1 V plus alpha 2 integral on ID of A U2 V. So this is going to give me interval RD of alpha 1 a u1 plus alpha 2 a u2 v, right? So now, which means that, okay, I'm gonna have the interval RD. So this is the interval RD of a alpha 1 u1 plus alpha 2 u2 v times v will be the interval RD of alpha 1 a u1 plus alpha 2 a u2 v. And this is true for all of the v in H. Right? So from this, how can I deduce the first one? My question is, so I explain again this step. Okay. If I fix u for any u, due to the Ritz theorem, there is a u such that this bilinear form can be written as the inner product of AU and V. All right? Now, I'm going to show that this A is linear in U. If I want to show that A is linear in U, by definition, what I have to prove is that I have to prove that A of alpha 1 U1 plus alpha 2 U2 will be alpha 1 A U1 plus alpha 2 A U2, right? For all of the U1 and U2 in H, and for all of the real numbers UV. All right? Now, to show this identity, what I have to do is I have to go back to the definition of the A, right? So the A is defined via this operator B, right? So AU V will be BUV, which means that A of alpha 1 U1 plus alpha 2 U2 V will be B of alpha 1 U1 alpha 2 U2 V. All right? Now, so in the previous step 1, what we used was the linearity of the B in V. But because B is a bilinear form, which means that this is linear in U, and this is also linear in V. Meaning that I can write B of alpha 1 U1 plus alpha 2 U2 V as alpha 1 B U1 V plus alpha 2 B U2 V. All right? Now I'm going to use the definition again. So B U1 V will be A U1 V, B U2 V will be A U2 V. So what is this inner product? Because I'm considering a special case in which H is L2. So this is inner product in L2 will be alpha 1 AU1V, alpha 2 AU2V. All right? So because this is an integral, I can group alpha 1 AU1, alpha 2 AU2V. Finally, what I obtain is something like this. I have A alpha 1 U1, alpha 2 U2, V is going to be the integral on RD of alpha 1 AU1 plus alpha 2 AU2 V for all of the V in H. What I want to show is that A alpha 1 U1 plus alpha 2 U2 is alpha 1 AU1 plus alpha 2 AU2. How can I show that? Right? So my question can be simplified in the following form. I have integral on RD of A alpha 1 U1 plus alpha 2 U2 V is going to be integral RD of alpha 1 AU1 plus alpha 2 AU2 V for all of the V. Right? Can I show that A of alpha 1 U1? Yes, so Jonathan got it correctly, right? So what? That will be the delta function. So Leo also has a very beautiful idea, yes. Plus alpha 2 AU2. So I want to show that this is this leads to this one, right? So there are two ideas. The first idea is by Jonathan, and the second idea by Liu. So both are very good idea. So the first idea would be the following. So this is true for all of the V in L2, right? Meaning that, okay, you're gonna have what? You're gonna have A alpha 1 U1 plus alpha 2 U2 minus alpha 1 A U1 minus alpha 2 A U2 is equal to. So I'm gonna subtract the right to the left. So then this is true for all of the V in L2. So now I call it the function f, right? So then what I have is that, okay, the interval idea of f v will be 0 for the f in h. So this is h, and f is a function in f in h as well, right? So Jonathan idea is the following: we subtract the left hand side, the left hand side and the right hand side. When we subtract the left hand side and the right hand side, what we get is the difference between this guy and this guy. I call it the f. So what we have is that, okay, we have a function f in the space h such that satisfy the condition that f times v is going to be 0 for all of the f, for all of the v in h. So we follow the ideas of the previous exercise. I'm going to choose v to be f, right? In this case, p is 2, right? Notice that in the previous exercise, we choose something like u to the power p minus 2u. So in this case, p is 2, right? Previous class. So p is 2, meaning that we choose u only, right? So in this case, we choose v to be f. What happened? Choose v to be f. What happened? We have that f times f is 0, meaning that interval d of f squared is going to be 0, right? Meaning that f squared is 0, meaning that f is 0, right? So which means that a alpha 1 u1 plus alpha 2 u2 is equal to alpha u1 plus alpha a u2, right? So there are two ideas. Jonathan and Liu's idea both are very good. So I explain again. I have a of alpha 1 u1 plus alpha 2 u2 v is equal to integral idea of alpha 1 a u1 plus alpha 2 a u2 times v, right? So this is true for all of the v in h, which is L2. Now what I want to show is that a of alpha 1 u1 plus alpha 2 u2 is going to be equal to alpha 1 a u1 plus alpha 2 a u2. How do I prove that? I subtract the right hand side to the left hand side. I call it f. So I reduce the question into the following. I'm going to have the integral on idea of the product of f times v is going to be 0. F is function in h, and this is true for all of the v in h. All right? So I'm going to choose v to be a special function, which is f. So when I replace this f into this guy, I'm going to have that the integral on idea of f times f is going to be 0, meaning that the integral on idea of f squared is going to be 0, meaning that f squared is 0 and f is 0. So when f is 0, a of alpha 1 u1 plus alpha 2 u2 is alpha 1 a u1 plus alpha 2 a u2, right? So the second idea is also very pretty, which is Liu's idea, right? So in this case, you're going to have what? You're going to have the of a of alpha 1 u1 plus alpha 2 u2 v d alpha 1 a u1 plus alpha 2 a u2 v. All right? So this is true for all of the v in L2. Again, you're gonna subtract it like in the previous exercise, previous approach, and you're gonna have what? You're gonna have that this is equal to 0 for all of the v in L2, right? So now you have a function f in L2, and if you multiply this function f with v for all of v in L2, then this is 0. So one idea is to choose v to be the delta function of for the x to be equal to a for arbitrary a, right? So what happened? So when you multiply this delta function into this f, right? So and then you integrate this with respect to x, right? So you multiply this with this test function, you have 0. But because this is delta function, this gives you fa, which means that fa is going to be 0. But you have to be careful because the delta function is not in L2, right? So you have to do some immediate, some right? So some extra steps. Right? So V is not in L2. V is a distribution, but this is not an L2 function. This is not a function. This is not a function. This is a distribution. So this works formally. This works formally. But in order to have something rigorous, you have to do some extra steps. So basically, what you do is what? What you do is you approximate this delta function by a smooth function, which is phi. So phi of epsilon. So basically, this is phi of epsilon, 1 over epsilon to the d. Right? So phi is a compactly supported function in RD. Right? So, all right. So what you do is that, okay, you're gonna approximate this delta function by the so-called the smooth approximation of this delta function. And this smooth approximation will be of the following form. You're gonna consider a compactly supported function, which is infinitely times differentiable. And then you scale it with respect to epsilon. Epsilon is a parameter, so you're gonna call it phi epsilon of x. So epsilon is the scale parameter, and epsilon is positive, and you're gonna send epsilon to 0. So when epsilon tends to 0, phi of epsilon of x is going to be delta of x to be 0, right? And then if you want delta of x to be a, then you're gonna shift this. But then instead of this delta function, what you do is that, okay, you're gonna multiply this with this phi epsilon x, which is CC infinity function, so it should be in L2. So this is, when epsilon tends to 0, this is also going to Fa, right? But because this is 0, Fa has to be 0. So this has to be 0, right? But this is more complicated, but I think the simpler way is the way of Jonathan, in which you just replace this V to be the difference between the two functions, right? This is nice, and this is, but indeed this is useful in other situation. This is very useful. This is a trick that you're gonna use a lot. But you have to remember that, okay, you want to multiply this with a delta function, so this is fine, this works formally, but to prove it rigorously, you need the help of this smooth approximation, right? So this is the modifier. So basically what you do is you pick a CC infinity function, you scale it with respect to a scale parameter epsilon, right? So then this is a smooth approximation of the delta function, right? So whenever you want to use the delta function, you have to approximate that by smooth function, and this is the modifier that you need to keep in mind. So basically, with this modifier, is going to be the delta function, and then everything now is safe. You multiply this modifier with f. You let the limit tend to 0, you get Fa. Then Fa is 0, meaning that f has to be 0, right? But this is a beautiful ideas, and it's if you do PDs, you're gonna have to use it a lot. Any questions? Right. Okay. Thank you. All right. So now let us continue. Right. So. Right. So what we show is that A is linear. So basically, if you have BUV, is going to be AUV, the axon, right? And then AUV is linear, meaning that, okay, A of alpha 1 U1 plus alpha 2 U2 is equal to alpha 1 A U1 plus alpha 2 A U2. All right. the first thing that you have is A is linear. And the second claim is that A is bounded. A is bounded. All right. So similar to B theorem. So how do I show that A is bounded? Right? So you're gonna have to bound the norm of A, right? So how do I bound the norm of A? Right? You're gonna go back to this this guy, and you're gonna use a symmetric to B theorem, even though this is a little bit more delicate. So the idea is to choose a smart test function v, right? So I'm going to choose a smart test function v such that when I plug this v here, I'm going to have what? I'm going to have that b uv, right? So I'm going to plug this smart test function here so that when I plug this smart test function here, this allow me to bound a u in the by some constant times u, right? So what kind of test function you want you can think of, right? So this is true for all v. So because this is true for all v, this is a very powerful fact, right? So the idea is that, okay, if you have something which is true for all of the v, you're gonna choose a test function v. So Liu has a good idea. So the first thing is v, the norm of v is 1. So Liu's idea. Right? So any suggestion for any other suggestion for v? So the first thing that, so suppose that the norm of v is 1. So suppose that we choose the norm of v is 1. You're going to have this. All right? But basically, this doesn't give you any information about the norm of A of u, right? Does it? No. Right? So even if you choose the norm of v to be 1, this cannot give you any information about the norm of A. Right? Any further suggestion? So hint. The hint that you have is, of course, the hypothesis that I gave you, right? So this is smaller than alpha of the norm of u times the norm of v, right? So from the beginning, we know that this bilinear form is bounded in the sense that the absolute value of buv is going to be smaller than alpha, the norm of u times the norm of v, all right? So all of those guys are in L2, right? So now you're going to have this boundedness, right? So the trivial bound that we get from this boundedness is that the absolute value of AUV is going to be smaller than alpha u, the norm of u times the norm of v. So can you suggest to me one special choice of v so that from this you're gonna get this inequality right away? Yes, so Lewis has a Lewis idea, right? So the second idea of Liu is the following. So you choose V to be a U, right? So basically, if something is true for all of the V, you just pick all of the special values of the vectors that you can think of. So the first thought of Liu is that, okay, you choose V such that the normal V is 1. It doesn't work. The second thought is that, okay, you choose a special value of V, which is AU. So when I plug AU there, what do I get? I have AU is smaller than the norm of u, so the norm of v will be the norm of AU. right? So what it is, this is AU square dx d. This is smaller than AU, right? So this AU square will be the norm of AU square, and this is smaller than the norm of U times the norm of AU, right? So I can divide the norm of AU on both sides. I'm gonna get the norm of AU is smaller than alpha the norm of U, and this means that this operator is bounded, right? I explain again. So you have an identity which is true for all of the V, right? So you want to extract some information from this identity. So the idea is, okay, you try to choose all of the special value of V and you plug it into this expression and you see what is going on, right? So this is an experiment. Now, the first idea by Liu is to choose a vector whose norm is 1, but when you plug it here, it doesn't work. The second idea is the special choice in which V is equal to AU. What happened? When I plug V here, I have AU is smaller than, okay, so this guy is smaller than alpha, the norm of U times the norm of V. So this is alpha, the norm of U times the norm of AU. So this is nothing but the norm of AU square. So the norm of AU square is smaller than the norm of U times the norm of AU, meaning that, okay, the norm of AU is smaller than alpha, the norm of U. And that's it. We show that alpha is bounded. All right. So in this lecture, we know that, okay, this AU is special, it is linear, and it is also bounded. So in the next class, we're going to study some special property of this AU, right? Any questions? If there's no questions, so we can continue this lecture on Wednesday. So, all right, so see you on Wednesday. Yes? See you on Wednesday. Bye. Have a nice afternoon.